guys. So what we're going to do today is we are going to look at complex numbers. So complex numbers include all the numbers that you've really seen so far this year, but they also include the new one we're going to look at today, which are imaginary numbers. And we'll get into that here in a second. So what we're going to do is we're going to look at number sets. So we'll start with this big red oval here. So this big red oval is the set of all real numbers. Okay, we've used that terminology before. A lot of times you've probably seen this little fancy script R that is a shortcut for writing all real numbers. And real numbers is really everything we've dealt with this year. There's the two biggest kind of subsets, or the bigger subset is rational numbers. And then if it's not a rational number, you can have an irrational number. So an irrational number is anything that cannot be written as a fraction. So an example of an irrational number, the square root of 3, 2 minus the square root of 5. A lot of those answers that you get solving a quadratic that you get from the quadratic formula. Another irrational number you guys have learned a lot about is pi. Okay, pi is an irrational number because there is no fractional equivalent. Now, 22/7 is pretty close, but it's not exact. There is no exact fraction that we can use to represent pi. Another one we'll do later this year is e. E is actually a constant as well, but we'll look at that second semester. Now, the big subset within real numbers are rational numbers. Okay, so rational numbers are any number that can be written as a fraction. So 7/3 is a rational number. 0.2 is a rational number because you can write that as 2/10 or 1/5. Negative 0.99999 is a rational number because you can write that as negative 9,999 over 10,000. Negative 20, 7, those are all rational numbers. And you'll notice within the set of rational numbers, you have these progressively smaller sets of numbers that are all rational. They all fall within the set of rational, but they get less or more and more specific as those circles get smaller. So the first one that's inside there is integers. So integers are all our positive and negative numbers. But these are positive and negative whole numbers. Okay, so negative 20, 14, those are integers. Okay, but 1/2 is not an integer. It's a rational number. Whole numbers, okay, it's basically 0, and then all the natural numbers, which are your whole positive numbers. Okay, so whole numbers have to be positive. And then natural numbers, we kind of use that as describing things in nature. Okay, you have 1 tree, you have 3 people. Okay, you don't have half a person or a third of a person. So those are your whole positive numbers. So that's our smallest set within that set of rational numbers. 0, it typically is not referred to as a natural number. There's a little bit of debate on that, but for here, we're going to say it's not we're going to say 0 is a whole number, not a natural number. All right, so all of the real numbers that we've looked at so far this year, those all fall under the big bubble of complex numbers. What also is a part of complex numbers is what we're going to look at today, which are called imaginary numbers. So what an imaginary number is basically the square root of a negative number. All right, so if you look over here in this box, this describes an imaginary number. Okay, so the square root of a negative. It's really easy to write this in this form. Basically, all you do is you take the negative out of the square root, you move it to the outside, and you make it an I. So the square root of negative 4 is I square root of 4, which we also could write as 2I. All right, so along those lines with that property, okay, if you square that, if you have I squared times the square root of R, that becomes a negative R. So I squared is a negative 1, and we'll use that property a lot this year. So complex numbers, when we talk about complex numbers, standard form for a complex number is in the form of A plus BI. So that's why both imaginary and real kind of fall into this category of complex numbers, because what you can do is you can write something like, you're going to see things come out as 3 plus 2I. Well, 3 is the real part of that complex number. 2I is the imaginary part of that complex number. All right, so before we get into complex numbers too much in depth, I want to go ahead and review rational operations. So how we work with our square roots. Irrational. Irrational numbers. Sorry about that. So operations with square roots. So let's make sure we remember this. You probably saw this in geometry, if not earlier. So we'll start with adding square roots. In order to add square roots together, you have to have the same number under the root. So I can add these together because they're both square roots of 5. When I add them together, 1 square root of 5 plus 3 square roots of 5 is 4 square roots of 5. All right, if you look at b in its current form, we cannot combine any of those together. But what I can do is I can simplify those square roots, and then I can combine them together. So square root of 8 becomes 2 root 2. Square root of 27 becomes 3 root 3. And square root of 12 becomes 2 root 3. Well, now, 2 root 2 minus root 2, that is just 1 root 2. And 3 root 3 minus 2 root 3, that is just 1 root 3. All right, when we multiply, okay, we'll just go ahead and distribute. Whenever you multiply a square root by another square root, they do not have to have the same number underneath. That's only for adding and subtracting. So since these are being multiplied, this can become the square root of 6. All right, so whenever you multiply the inside numbers together. If there was a number on the outside, you would also multiply the outside numbers together as well. Any inside numbers get multiplied together and stay inside. Outside numbers get multiplied together and stay outside. So same thing here. So when I do 3 times root 2, 3 is outside the root, square root of 2 stays inside. All right, let's look over here. Foiling. Okay, so 2 times 3 is 6. 2 times a negative root 5 would be a negative 2 root 5. This becomes minus 3 root 3. And this becomes plus the square root of 15. None of those can be simplified. None of those can be combined together. So that's as far as we can go. All right, then finally on E, you probably learned about this one about how to rationalize the denominator. So rationalizing the denominator is when you get the square root out of the bottom. It's not always required, but it is a good idea, typically because you won't see multiple choice answers that have denominators that are not rationalized. So what you do is you multiply by something called the conjugate in this case. And the conjugate would be 1 plus the square root of 2. The reason you multiply by 1 plus the square root of 2 top and bottom is because when you FOIL this out, okay, you'll notice really what this is a difference of squares. It's the same thing, 1's plus, 1's minus. So when you multiply out the bottom, 1 times 1, positive root 2 and negative root 2 end up in the middle, which obviously cancel out. And then you have negative root 2 times root 2, which is just regular 2. Those middle terms cancel. You're left with just 1 minus 2, which at the bottom then is just a negative 1. At the top, I have 3 plus 3 root 2. Since I'm dividing by negative 1 then, I can write that as negative 3 minus 3 root 2. And now this is rationalized. Now that idea of multiplying the conjugate is going to be important later on here. We'll use that for our complex numbers. All right, so again, this is just looking at imaginary numbers. Now, very, very simple. Like I said, if there's a negative on the inside, you basically move it to the outside and it becomes an I. So this becomes I square root of 25. Well, to really simplify this, we know the square root of 25 is 5. So this is really 5I. All right, the square root of negative 20, that is I times the square root of 20. Square root of 20 can simplify to 2 root 5, so this is 2I root 5. Square root of negative 72, all right, that is divisible by 36, so that becomes 6I root 2. Square root of negative 11 does not simplify, so this just becomes I root 11. So again, very easy to work with. Negative on the inside becomes an I on the outside. All right, so now let's look at a couple powers of I. All right, so we said from that first property at the beginning, I squared is negative 1. And that's an important one. You're going to see this come up a lot, okay? I squared is negative 1. Well, now let's look at I to the third. I to the third, if we use our exponent properties, that's I times I squared, which means it's I times negative 1, which means it's negative I. So I cubed is negative I. All right, let's look at I to the fourth. I to the fourth, using exponent properties, is I squared times I squared. Well, I squared is negative 1. Negative 1 times negative 1 is 1. So what this tells us, okay, is that we have I to the first is I squared is negative 1. I to the third is negative I, and I to the fourth is 1. Every other I raised to some power is going to be one of these four things. Because think about it, let's say if we go to the next one, if I go to I to the fifth, well, that is I times I to the fourth. Well, I to the fourth is 1, so it's just I. If I do I to the sixth, that's I squared times I to the fourth. I to the fourth is just 1, same thing as I squared. I to the seventh, okay, I cubed times I to the fourth, and hopefully you're starting to see the pattern. That's just 1, so I to the seventh is the same thing as I to the third, which is -1. So what we're going to do is we're going to simplify some of these higher powered i's. All right, I to the 16th. So since we know I to the fourth power is 1, we need to think, hey, is this a multiple of 4? And if not, what's the closest multiple of 4 below it? Well, I to the 16th is a multiple of 4. That means it's I to the fourth times I to the fourth times I to the fourth times I to the fourth. Or an easier way to write that, I to the fourth to the fourth. I to the fourth is just 1. 1 to the fourth is just 1. So this whole thing is just 1. So moral of the story here, if that's divisible by 4, it's equivalent to 1. All right, well, let's look at one that's not divisible by 4. I to the 23rd. What we're going to do is we're going to find the closest multiple of 4 without going over. Well, that would be 20. So I to the 23rd, that's I to the 20th times I to the third. Well, I to the 20th, that's multiple of 4. That means that this whole thing is just 1. So all I have left then is I to the third. I to the third is -I. All right, I to the 82nd. Not divisible by 4, but I to the 80th is. That leaves me with just I squared, and I squared is the same thing as -1. So whenever you have I to the something power, okay, you're going to get basically one of these 4 things. I, -1, -I, or 1. All right, when it comes to graphing complex numbers, they actually have their own coordinate plane. They do not graph on the XY axis. What you have is a real axis and an imaginary axis. Now, this is not really that big of an important part of complex numbers. It's just something so you guys can see. This is kind of how you would plot these. This is not the most important thing we're doing today. So 2 plus 3i, again, this is just reinforcing the fact that you have a real component and an imaginary component. So if I were to graph 2 plus 3i, I would go over to 2 and up to 3 on the imaginary axis. And that point right there would be 2 plus 3i. -3 minus 3i, -3 on the real axis, -3 on the imaginary axis. 3i, just up 3 on the imaginary axis. What you can also do is find the absolute value. Again, absolute value is a little bit different. It's the distance it is away, not from 0, but from the origin on this complex plane. So for 3i, that's pretty easy. Okay, that distance right there is 3. So the absolute value of 3i is 3. All right, let's look at the next one though, 2 plus 3i. So 2 plus 3i, I'm looking for this distance. Well, you can use your distance formula, which is kind of what this is set up, or what you can consider the fact is this is basically a right triangle. All right, so you have 2 on the real side, 3 on the imaginary side, 2 squared plus 3 squared, the square root of that is your absolute value. That is the hypotenuse. That's the distance that point is away from 0. So that's 4 plus 9, so that's the square root of 13. Same thing, -3 minus 3. I've gone down 3 this way, I've gone over 3 this way, but when I square those, they're still going to be positive when I square it. So that becomes the square root of 18, which is 3 root 2. You also may recognize that that is a special right triangle, so you may not even need Pythagorean theorem in that case. Again, that little section, not the most important thing from today, just kind of some things that will come up later on in some future math classes for you. All right, so now we're going to look at operations. Adding and subtracting complex numbers is incredibly easy. You literally, if you didn't know what I was, you could still do this operation because you're just combining like terms. All right, so there's nothing different when you add and subtract. So combine the real parts together, combine the imaginary parts together, done. When you're subtracting, just make sure, don't forget to distribute that negative. Don't let that be the reason you miss this. So this becomes -2 minus 3, that's the real part. 5i minus -2i, that's the imaginary part. So that becomes -5 plus 7i. Typically, when we write our answer, we're going to write it in standard form, which is that a plus bi form. So you have the real part together and you have the imaginary part together. All right, looking at the next one, FOIL it out. So that becomes -9 minus 3i plus 3i plus I squared. All right, so this is slightly different than just combining like terms. Well, obviously negative 3i plus 3i cancels out. But what we need to do here, whenever we multiply, consider that I squared is negative 1. So this becomes negative 9 minus 1, which is negative 10. All right, on D, if you feel comfortable, pause the video, try these next two on your own. Okay, 3 times 3 is 9, plus 12i, minus 12i, minus 16i squared. Again, the middles cancel out. The reason for that, think about it, these last two problems that we just did were difference of squares, okay? With difference of squares, those middles cancel out. This one, if it's hard to see, you could rewrite that first one as I minus, you can write that, sorry, I minus 3 and I plus 3. That makes it a little easier to see it's a difference of squares. Okay, so now to simplify this, I squared is negative 1. That means that minus 16i squared is actually 9 plus 16. All right, looking at the next one, 6 plus 2i minus 15i minus 5i squared. Minus 5i squared becomes negative 5 times negative 1. That becomes plus 5. 6 plus 5 is 11. 2i minus 15i is a negative 13i. All right, now this last one has a little bit of a trick to it. What we need to do, we cannot multiply this in its current form. If we do, we'll make a little small mistake and get the wrong answer. I cannot multiply these together the way they're written. I need to rewrite them as imaginary numbers first. And now I can FOIL this out. So this one's going to get a little messy, but it's kind of some good practice with multiplying our irrational numbers. So 2 times 3 is 6, minus 2i root 3, plus 3i root 2, minus I squared root 6. So minus I squared root 6 becomes just plus 1, so just plus root 6. I'm going to put the real parts together and the imaginary parts together. And this is as far as we can simplify this problem. Now, another way you could write this, or a way you may see this written, is you factor out whoops, I shouldn't have made that. There we go. You can factor out those coefficients of the i's. That way you know that is how much your imaginary component is. Now, it just kind of depends. Really, where that factor would come in is if you see this as a multiple choice type question. Okay, you may not see this answer. You may see this answer. So just getting used to kind of how you can write these in some different forms. There's nothing wrong, though, with leaving it in this form. All right, so the other operation that we do, it's not really division, but what we really do is we rationalize these ones if you have an I in the denominator. And what we do is the same thing you did at the very beginning with the irrational numbers. You multiply by the complex conjugate. And conjugate just means the opposite sign in the middle, okay, the opposite sign in the middle. Because what that does is it creates a difference of squares. So the complex conjugate of 3 minus 4i is 3 plus 4i. So I'd multiply both the top and the bottom. So then I would FOIL this out to the top. That would become 30 plus 40i. And then at the bottom, I'll FOIL that out. The reason you're multiplying by the complex conjugate is because, again, that creates a difference of squares. Those middle terms are going to cancel. Negative 12i plus 12i cancels out. So all I have is 3 times 3, which is 9, minus 16i squared. Minus 16i squared, we know that becomes plus 16. 9 plus 16 is 25. And I'm going to write this final answer in that a plus bi form. So divide both things by 5. So 30 divided by 5 is 6 over 5 plus 8 over 5i. All right, let's look at b. So the complex conjugate would be 2 minus root 3i. FOIL at the top, or distribute the top, really. Then at the bottom, that would become 4. The middles would cancel because we're creating a difference of squares. And then this would become minus root 3 times root 3 would be 3i squared. 3i squared becomes plus 3. So that becomes 4 plus 3, which is 7. So then if you leave it in that form, there's nothing wrong. If you want to write it in standard form, 6 over 7 minus 3 root 3 over 7i. Standard form is just nice because it makes it really clear what the real part is and what the imaginary part is. All right, again, if you feel comfortable, pause the video, try these next two on your own. All right, we're going to multiply by the conjugate. That gives you 6 minus 2i minus 3i is minus 5i plus i squared at the top. On the bottom, that becomes 4 minus i squared. So we'll simplify. That becomes 6 plus i squared becomes minus 1. So that becomes 5 minus 5i. Minus I squared becomes plus 1, so that becomes 4 plus 1, which is 5. So this becomes 1 minus I. And then on this last one, you actually have two options. If you want, you can multiply this by top and bottom by positive 3i or negative 3i. You'll still end up getting that I out of the denominator either way. So I'll just do negative 3i because that's kind of what we're used to. So that gives me negative 9i plus 3i squared over negative 9i squared. Negative 9i squared is just going to become 9. This would then become negative 3 minus 9i. And then I can simplify this to negative 1/3 minus I. All right, so the last thing that we're going to use complex numbers for is now when we solve quadratics. In the past, if we solved quadratics, we would just write the real solutions. Well, now we can find all solutions, including any complex or imaginary solutions. So we're going to start by solving this quadratic. You can use whatever method you want. Factoring won't work. But I'm going to use completing the square just because it's my opinion that if you have an a value of 1 and a b value that's even, I think completing the square is the fastest option. It's also just good review. So this becomes x squared. So for completing the square, I'm going to start by leaving a blank and moving the 13 to the other side. To figure out what goes in that blank, take the middle number, divide it by 2, and square it. And remember, if it's on the other side, they're going to add it on both sides to keep that equation balanced, not changing in any way. All right, so now that left side is a perfect square trinomial, factors into x minus 3 squared. Negative 13 plus 9 is a negative 4. At this point, I can square root both sides. The square root of negative 4 would be plus or minus, because we're taking that square root. Square root of negative 4 would be plus or minus 2i. So add that 3, I end up with 3 plus or minus 2i. So again, I do think completing the square is a little bit of a faster method for these quadratics. Again, when a is 1 and when b is an even number. All right, so now let's look at this next one. Now this isn't really a quadratic. This is actually kind of a preview for what you guys are going to see in the next unit over polynomials. Now, our first step here is still going to be the same. I still want to start by setting this equal to 0. And since it's not quadratic, I can't really use quadratic formula. And that's the reason I wanted to pull this one up, is because that's a really common mistake here. Now, if you use quadratic formula, it is possible to still solve it. And I'll show you that in a second. But really, the fastest way and the easiest way to solve this is to factor. And that's why I wanted to look at this example, because this is factorable. All right, we can figure out what multiplies to a negative 15 and adds to a negative 2. Keep those variables the same, so this would become x squared minus 5 and x squared plus 3. Well, now if I want to solve this, I can solve it pretty easily. Take each factor, set each factor equal to 0. So you can set each factor equal to 0 then. So I get that x squared is equal to 5, so x is equal to plus or minus the square root of 5. Over here, x squared is equal to negative 3, which we now know we can find the imaginary solution for. So plus or minus the square root of negative 3, which is plus or minus I root 3. Again, we'll see this more when we get to polynomials, so this is really just kind of an introduction. Really what I want to focus on here is the factoring, because that's something that we have done so far in this unit. The other thing I wanted to hit on is the fact about the quadratic formula. So quadratic formula, this is not quadratic, okay? Remember, quadratic formula, you would have to say that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. But that would give us our answers to a quadratic. What we could do, though, is we could rewrite this, and we can let x squared replace that x basically in this equation. So I'll use a different variable here. I'm going to use u. So I'm going to let u stand for x squared. If I do that, I can rewrite this problem as u squared minus 15u minus 2u minus 15. So now that's the same as this equation, but I've replaced an x squared with u. And the reason I'm using u, it's just a different variable, because if I use x again, it can get a little tricky. That's just a different variable. That variable in particular is one you'll see later on. Then what I can do is now this is quadratic. So I can go ahead and solve that with quadratic formula. All right, so negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is 2 plus or minus, that's going to be the square root of 64 over 2. So that's going to be 2 plus or minus 8 over 2. We can actually find those values. 2 plus 8 is 10. 10 divided by 2 is 5. And 2 minus 8 over 2, that's going to be a negative 3. But what we have to keep in mind, okay, that's really not x. I shouldn't have used x there. That's what u is. So u is 5 and u is negative 3, because those are solutions to this quadratic. X, remember, was replaced here. So I get x squared is equal to 5 and x squared is equal to negative 3. So x equals plus or minus root 5 and x equals plus or minus negative root 3, which are the same answers that I got previously. So if you're using quadratic formula, make sure that it's actually quadratic. That's kind of the moral of the story here. This was not quadratic. And again, this is a polynomial. We'll see these more later in the next unit. I was trying to get you guys a little bit of early exposure to this. All right, so that's it for complex numbers. Again, just keep in mind, basically, if you have a negative inside the square root, move it to the outside and change it to an I. And that's kind of the big thing here. Also remember that I squared is a negative 1.